Imaginary numbers are one of the most fascinating concepts in mathematics, extending our number system beyond what we can physically count or measure. Consider this intriguing equation: x squared equals -1. At first glance, it might seem like a simple problem to solve. But there's a fundamental challenge here. What number, when multiplied by itself, gives us -1? If we think about the numbers we're familiar with, this seems impossible. To understand why, let's examine what happens when we square different types of numbers. When we square a positive number like 3, we get 9, because 3 times 3 equals 9. What about negative numbers? When we square -3, we also get positive 9. This is because -3 times -3 equals positive 9, following the rule that a negative times a negative gives a positive. The same pattern holds for any real number. 5 squared is 25, and -5 squared is also 25. No matter what real number we choose, positive or negative, its square will always be positive or 0. This reveals a fundamental property. Any real number squared is always greater than or equal to 0. It can never be negative. This creates a dilemma for our equation x squared equals -1. Within the realm of real numbers, this equation simply has no solution. We've reached a limitation of our number system. To overcome this limitation, mathematicians took a bold step. They invented a new number called I, defined as the square root of -1. This wasn't just a notation trick. It was an expansion of our entire number system. By definition, when we square I, we get -1. This is what makes I different from any real number. It's the only number that, when squared, gives us -1. It exists outside our real number line. And just like that, our original equation x squared equals -1 now has a solution: x equals I. We've solved a previously unsolvable equation by expanding our concept of what numbers can be. With the imaginary unit I, we can now express the square roots of any negative number in a consistent way. This opens up a whole new family of numbers called imaginary numbers. For instance, the square root of -4 equals 2i, because 2i squared equals -4. Similarly, the square root of -9 is 3i, the square root of -16 is 4i, and the square root of -25 is 5i. In each case, we're finding the positive number that, when multiplied by I, gives us the square root of a negative number. Imaginary numbers fundamentally expand our mathematical toolkit. They allow us to solve equations that were previously considered impossible, opening doors to new mathematical insights and applications in physics, engineering, and many other fields. Let's explore the powers of I, the imaginary unit, a number defined by the property that when squared, it equals -1. The first power of I, or I to the first, is simply I itself, just like any number raised to the power of 1. When we square I, or raise I to the power of 2, we get I times I. By the very definition of I, this equals -1, which is what makes I so special. For I cubed, we multiply I squared by I again. Since I squared equals -1, we have -1 times I, giving us -I. This is our third value in the pattern. When we take I to the fourth power, we multiply I cubed by I. Since I cubed is -I, we have -I times I. This gives us -I squared. And since I squared is -1, -I squared is negative of -1, which equals +1. Notice the fascinating pattern we've discovered. Starting with I, then multiplying by I repeatedly, we cycle through 4 distinct values: I, -1, -I, and then back to 1. After 4 multiplications, we return to our starting point. This cyclic behavior can be beautifully visualized as points on a circle. In fact, this representation reveals a deep connection between complex numbers and rotations in the plane. Each time we multiply by I, we effectively rotate counterclockwise by 90 degrees around the origin. This is a geometric interpretation of multiplication by I. It's a rotation operator in the complex plane. Let's watch this pattern in action. Starting at 1, each multiplication by I rotates us 90 degrees counterclockwise. from 1 to I, from I to -1, from -1 to -I, and finally from -I back to 1. This cycle continues indefinitely. If we were to calculate I to the 5th power, we'd get I again, since I to the 4th is 1, and 1 times I is I. Similarly, I to the 6th would be -1, I to the 7th would be -I, and so on. For any power of I, we can determine its value by dividing the exponent by 4 and looking at the remainder. If the remainder is 0, the result is 1. If it's 1, the result is I. If it's 2, we get -1, and if it's 3, we get -I. This cyclic pattern is what makes imaginary numbers so useful in fields like signal processing, electrical engineering, and quantum mechanics. The regular, predictable rotations of I allow us to model periodic phenomena in a natural way. Let's explore the fascinating pattern of powers of I, the imaginary unit. One of the most useful properties of I is that its powers follow a predictable cycle of 4. I to the 1st power is simply I itself, the fundamental imaginary unit defined as the square root of -1. When we square I, we get I squared, which equals -1. This follows directly from the definition of I as the square root of -1. I cubed, or I to the 3rd power, equals -I. We can verify this by multiplying I squared, which is -1, by another I, giving us -I. Finally, I to the 4th power equals 1. This happens because I to the 4th is I squared times I squared, which is -1 times -1, resulting in +1. This cycle of 4 values, I, -1, -I, and 1, repeats indefinitely as we continue to higher powers. This cyclical nature gives us a powerful shortcut for calculating any power of I without tedious multiplication. Let's apply this pattern to find I to the power of 7. Instead of multiplying I by itself 7 times, we can use the cycle of 4 to simplify our work. The key insight is to divide the exponent by 4. When we divide 7 by 4, we get 1 with a remainder of 3. This remainder tells us which position in our cycle corresponds to I to the 7th power. We can express I to the 7th as I to the power of 4 times 1 plus 3, which equals I to the 4th times I to the 3rd. Since I to the 4th equals 1 and I to the 3rd equals -I, the result is -I. This is much faster than calculating 7 consecutive multiplications. Looking at our cycle, we can confirm that I to the 7th corresponds to the 3rd position, -I. The remainder 3 tells us to look at the 3rd position in our cycle. Let's try a larger exponent, I to the power of 15. With high powers like this, our cyclical method becomes even more valuable. Dividing 15 by 4, we get 3 with a remainder of 3. Again, this remainder is the key to our solution. We can rewrite I to the 15th as I to the power of 4 times 3 plus 3. This equals I to the 12th times I to the 3rd. Since I to the 12th is the same as I to the 4th cubed, which is 1 cubed or just 1, we multiply 1 by I to the 3rd power, -I, giving us -I as our answer. Once again, the remainder of 3 directs us to the 3rd position in our cycle, which is -I. Notice that I to the 15th and I to the 7th have the same value, as both exponents leave the same remainder when divided by 4. For our final example, let's find the value of I to the power of 20. This example will show us what happens with exponents that are multiples of 4. When we divide 20 by 4, we get exactly 5 with no remainder. A remainder of 0 is significant because it means the exponent is a multiple of 4. We can write I to the 20th as I to the power of 4 times 5 plus 0. This is equivalent to I to the 20th times I to the 0th. Since I to the 20th can be rewritten as I to the 4th to the 5th power and I to the 4th equals 1, we have 1 to the 5th power times I to the 0th, which is 1 times 1, giving us 1. When the remainder is 0, we effectively complete a full cycle. Since I to the 4th equals 1, any power of I that's divisible by 4 will equal 1 as well. This is because 1 raised to any power remains 1. Looking at our cycle, a remainder of 0 corresponds to the fourth position, which is 1. Any power of I that gives a remainder of 0 when divided by 4 will equal 1, just as I to the 4th, 8th, 12th, 16th, and 20th all equal 1. This method works for any power of I. Simply divide the exponent by 4, find the remainder, and use the corresponding value in our cycle. The remainders 0, 1, 2, and 3 correspond to the values y, -1, and -I, respectively. This pattern makes calculating powers of I remarkably straightforward. Complex numbers are a fascinating extension of our number system, allowing us to work with mathematical concepts that aren't possible with real numbers alone. A complex number z can be written as a plus bi, where a is the real part shown in blue, and b is the coefficient of the imaginary unit I shown in red. The imaginary unit I is defined as the square root of -1. Here are 3 examples of complex numbers. In 3 plus 2i, 3 is the real part and 2 is the coefficient of I. In -4 minus 7i, -4 is the real part and -7 is the coefficient of I. And in 2 minus 3i, 2 is the real part and -3 is the coefficient of I. Let's explore how to add complex numbers. The key insight is that we add the real parts together and the imaginary parts together separately. For this example, let's add 3 plus 2i and 1 plus 4i. We treat complex numbers like binomials, adding the corresponding parts together. For the real parts, we add 3 plus 1 to get 4. For the imaginary parts, we add 2i plus 4i to get 6i. This gives us a final result of 4 plus 6i. Subtraction follows the same principle as addition. We subtract the real parts from each other and do the same with the imaginary parts. Let's subtract 1 plus 4i from 3 plus 2i. We'll subtract the real parts from each other and do the same with the imaginary parts. For the real parts, we calculate 3 minus 1, which equals 2. For the imaginary parts, we have 2i minus 4i, which equals -2i. Our result is 2 minus 2i. Multiplication of complex numbers is more intricate than addition or subtraction. We'll need to use the distributive property and remember that I squared equals -1. To multiply two complex numbers in the form a plus bi and c plus di, we multiply each term in the first expression by each term in the second, just like when multiplying binomials using the FOIL method: first, outer, inner, last. The crucial step is recognizing that I squared equals -1, so we can replace bdi squared with bd times -1. After combining like terms, we get a more compact formula. The real part of the product is a c minus bd, and the imaginary part is a d plus bc. This formula lets us multiply any two complex numbers efficiently. Let's apply this to a concrete example, multiplying 2 plus 3i by 1 plus 2i. We'll work through this step by step. First, we multiply each term in the first parentheses by each term in the second. That's 2 times 1 plus 2 times 2i plus 3i times 1 plus 3i times 2i. Simplifying these products gives us 2 plus 4i plus 3i plus 6i squared. Notice how the first term is purely real, the middle two terms contain I, and the last term contains I squared. Now comes the key insight. I squared equals -1. So 6i squared becomes 6 times -1, or -6. This simplifies to 2 plus 4i plus 3i minus 6. Now we need to combine like terms. For the real part, we have 2 minus 6, which equals -4. For the imaginary part, we have 4i plus 3i, which equals 7i. So our final answer is -4 plus 7i. Complex numbers give us a powerful framework for working with quantities that involve the square root of negative numbers. Through operations like addition, subtraction, and multiplication, we can manipulate these numbers just as we do with real numbers, following certain special rules. Let's explore the complex plane, which gives us a powerful geometric way to visualize complex numbers as points in a two-dimensional space. In this coordinate system, the horizontal axis represents the real part of a complex number, while the vertical axis represents the imaginary part. This allows us to map any complex number of the form a plus bi to a unique point on the plane. Unlike real numbers that exist on a one-dimensional number line, complex numbers require this two-dimensional representation because they have both real and imaginary components. Each point on this plane corresponds to a unique complex number of the form a plus bi. Let's plot several complex numbers to see how they appear on the complex plane. This will help us develop an intuition for how complex numbers exist geometrically. Here's the complex number value, which we plot at the point x, y. The first coordinate x is the real component, and the second coordinate y is the coefficient of the imaginary component. Now let's examine the complex number 3 plus 2i more closely to understand the fundamental properties that all complex numbers possess. These properties reveal why the complex plane is such a powerful tool for understanding complex arithmetic. Every complex number has two essential characteristics that define its position and behavior: its magnitude, which tells us its size or length, and its argument, which tells us its direction or angle on the complex plane. The magnitude, also called the absolute value or modulus, represents the distance from the origin to the complex number's position on the plane. It tells us the size of the complex number, analogous to how we think about the absolute value of real numbers. For our complex number 3 plus 2i, we can calculate the magnitude by applying the Pythagorean theorem, since the real and imaginary components form the legs of a right triangle. To find the magnitude, we take the square root of the sum of the squares of both components. For 3 plus 2i, that's the square root of 3 squared plus 2 squared, which equals the square root of 9 plus 4, or the square root of 13, approximately 3.61 units. This is the distance from the origin to our complex number. The second key property is the argument, which represents the angle that the complex number makes with the positive real axis. This angle tells us the direction of our complex number on the plane. For our complex number 3 plus 2i, the argument theta is calculated using the inverse tangent function. Since the imaginary part is 2 and the real part is 3, we compute the inverse tangent of 2 divided by 3, which gives us approximately 33.7 degrees. This is the angle our complex number makes with the positive real axis. These two properties, magnitude and argument, allow us to represent complex numbers in what's called polar form. Instead of writing a complex number as a plus bi, we can express it as r times e raised to the power of I theta, where r is the magnitude and theta is the argument. This polar representation is particularly useful for understanding multiplication and exponentiation of complex numbers. When we multiply two complex numbers, their magnitudes multiply and their arguments add, a property that's much easier to visualize on the complex plane than in the standard a plus bi form. Looking back at our plot, we can see that the magnitude of each complex number is simply its distance from the origin. This geometric interpretation gives us an intuitive way to understand the absolute value of any complex number, regardless of which quadrant it's in. Similarly, the argument tells us the direction of the complex number on the plane. As we move around the origin, the argument changes, completing a full 360 degrees as we make one complete revolution. This helps explain why complex numbers are so useful in describing rotations and periodic phenomena. The geometric interpretation of complex numbers on the complex plane helps us visualize many properties that would be difficult to understand algebraically. This representation bridges algebra and geometry, making operations like addition, multiplication, and finding powers of complex numbers more intuitive. Let's explore a fundamental example of where imaginary numbers naturally arise. We'll solve a quadratic equation that leads to solutions involving imaginary numbers. To find the values of x that satisfy this equation, we'll use the quadratic formula. This formula works for any quadratic equation in the form ax squared plus bx plus c equals 0. Looking at our equation, x squared plus x plus 1 equals 0, we can identify the coefficients by comparing with the standard form. Here a equals 1, b equals 1, and c equals 1. The key to understanding the nature of our solutions lies in the discriminant, which is b squared minus 4ac. The discriminant tells us how many real solutions exist. If it's positive, we have 2 real solutions. If it's 0, we have 1 real solution. And if it's negative, we have no real solutions. Our discriminant is -3. This is significant because a negative discriminant means we'd need to take the square root of a negative number, which isn't possible in the realm of real numbers. In the real number system, which includes numbers like 2, -5, and the square root of 2, this equation would have no solutions. This is because we can't find a real number that, when squared, gives a negative result. But mathematics doesn't stop at real numbers. We can extend our number system by defining the imaginary unit I, where I squared equals -1. This allows us to express the square root of -3 as I times the square root of 3. Since the square root of -3 equals I times the square root of 3, we can rewrite our solution in a more standard form with the real and imaginary parts clearly separated. We now have 2 distinct solutions. When we choose the plus sign, we get x equals -1/2 plus square root of 3 over 2 times I. When we choose the minus sign, we get x equals -1/2 minus square root of 3 over 2 times I. Notice that these solutions differ only in the sign of their imaginary part. To better understand these complex solutions, let's visualize them on the complex plane. This will help us see the geometric relationship between these 2 values. The complex plane is a 2-dimensional coordinate system where we can plot complex numbers. The horizontal axis represents the real part, and the vertical axis represents the imaginary part. For example, the complex number 3 plus 2i would be plotted at the point with coordinates 3, 2. Let's plot our first solution, -1/2 plus square root of 3 over 2i. The real part is -1/2, and the imaginary part is square root of 3 over 2, which is approximately 0.866. So we place this point at coordinates -0.5 and 0.866. Now let's plot our second solution, -1/2 minus square root of 3 over 2i. This point has the same real part, -1/2, but its imaginary part is the negative of the first solution, so -0.866. These 2 points demonstrate an important property of quadratic equations with real coefficients. When they have complex solutions, these solutions always come in conjugate pairs. The complex conjugate of a number has the same real part, but the opposite imaginary part. This symmetric relationship is a direct consequence of the fact that our original equation had only real coefficients. This example illustrates why imaginary numbers are so valuable in mathematics. They allow us to find solutions to equations that would otherwise have no solutions within the real number system. Without imaginary numbers, many problems in physics, engineering, and mathematics would remain unsolvable. The introduction of complex numbers completes our number system in a profound way. The fundamental theorem of algebra states that with complex numbers, every polynomial equation has exactly as many solutions as its degree, counting multiplicities. Our quadratic has degree 2, and indeed we found exactly 2 complex solutions.